right, let's begin. So thank you everybody for coming to my talk. I'll skip over this intro, but today I'll be walking you through a portion of my master's thesis. So I have two goals for this talk. My first goal is to communicate the importance of knowing your data before starting your analysis. And the second lesson I want to leave you is the importance of first starting with a mathematical model and framework before diving into your data and trying to fit a model to your data. So for that end, I'll be walking you through a data modeling problem. For that, I'll be using data from a trial in London. This trial is going to take a subset of houses in London through a particular pricing model. And the question is, what is the effect of that pricing model on the consumption of those households? The outline for my talk is first we'll go through the problem space and define some terminology that is going to be helpful along the way. Then we'll go through the trial and the data set. We'll construct a mathematical model that is going to help us. Then we'll go through data prep, cleaning, processing, and analysis. And finally, we'll look at the results, conclusion, and some takeaways. So let's start with some useful details that are going to be helpful. And you might be asking, why is this pricing model going to affect consumption? So electricity is unique in that its storage is prohibitively costly. So what that means is that supply and demand must meet at all times. So imagine a state where you have demand exceeding supply. In that situation, you're going to have a power outage. Power outages are considered to be extremely costly, and so we try to prevent them as much as possible. So this unique feature of electricity poses some challenges. One of these challenges is, imagine you have an unpredictably hot day, there's unexpected demand on the grid, right? So you have more demand on the grid than you expected. In that situation, you're at the risk of a power outage. And so this particular feature of electricity makes it necessary to have close to real-time methods to reduce some of that demand on the grid. So one of these methods is called demand response. So as the name suggests, you're responding to that unexpected demand. So let's go through this visually and create some sort of an intuition. So if you look at 4 p.m., the blue line is telling you how much consumption or how much usage is on the grid. So at 4 p.m., there's quite a bit of demand on the grid, and it's also peaking. And so in that situation, this triggers a demand response event, and the shaded green region is the effect of the demand response event. So that's the amount of load reduction that you get as a result of demand response. So demand response can take different ways. So you've seen this old school method of demand response. It's those blast texts that you may have gotten on a hot day. So implicit in this assumption in demand response is that there's some fraction of the demand that is on the grid that can be shifted around, right? So we just need to use some tool to incentivize people to shift some of that demand around. So another way to do demand response is use a pricing model. So let's say we have a lot of demand on the grid and we want to incentivize people to consume less, right? Turn down that electricity, maybe do their wash their clothes at a different time. And so these pricing models increase the price in those times of high demand, and they assume that people are price sensitive, and so they're going to respond to this price incentive, and as a result of that, lower their consumption. There's two pricing models in demand response that are used quite often. One is time of use pricing. So time of use pricing has price bands that are preset, and times of day that are preset that's going to be implemented. So let's say from 6 p.m. to 8 p.m. every single day, the price of electricity is going to be double other times. So that's a time of use pricing model. A dynamic time of use pricing model has price bands that are preset, but the time that they are going to be implemented is dynamic and changes day over day. So dynamic time of use pricing is the pricing model that is implemented in this trial, and it's going to be that pricing model whose effect we're going to try to understand on the consumption of this subset of houses. Okay, so let's create our problem statement and make that more specific. So given the goal of demand response, we want to lower consumption in those times of high demand, right? And so the effect that we want to analyze is whether this pricing model is going to shed demand in those specific times. So it is not in aggregate that we want to lower consumption, it is in times of high demand that we want to lower consumption. So in this problem, we are trying to understand the causal effect of this pricing model on consumption. So with that, let's try to understand causality and some terminology around that. So let's assume that I wake up this morning and I have a headache. So I decide to take a headache pill, I have a talk, and I wait a little bit and my headache gets better. So the pill that I'm taking, that's the treatment. So in this scenario, that's called the treatment or the intervention. In the case of our trial, the pricing model is the treatment or the intervention. So treatment doesn't necessarily need to be an actual medical treatment. It is the thing whose impact on some other thing we're trying to measure. So the treatment effect is going to be how much my pain has gone away or how much consumption has been lowered as a result of this pricing model. I am in this situation the unit undergoing treatment, and this just means a single entity that we are analyzing as opposed to, for example, a population. So in this scenario, we're assuming that the headache pill has a causal effect on the amount of pain that I'm feeling. Similarly, we are assuming that the dynamic time of use pricing has a causal effect on consumption. And lastly, there's a reality in which I wake up in the morning, I have a headache, I simply have some water and wait, and my headache gets better. But that's a reality that has not been lived. So we don't know what would have happened and how my head would feel if I had not taken the pill. And so in that situation, that unlived reality is called the counterfactual state. It is not observed, it cannot be measured, so it's just something that could have happened, but we just don't know. So let's put some math to what we just talked about. Let's assume x to be a binary causal variable. So that means it can take two values. It can take a value 0 or 1. And so in the example that I just gave, x equals to 0 is me not taking the headache pill, and x equals to 1 is me taking the headache pill. Or x equals to 1 in our trial is going through dynamic time of use pricing, and x equals 0 is going through flat pricing. And take y to be the response variable. So the response variable in this situation is going to be the consumption of these households. And in the case of the example that I gave, is the level of pain that I'm feeling. And so we're assuming that x has a causal effect on y. Take y0 to be the value of y when x is equal to 0, and y1 to be the value of y when x is equal to 1. So here, the treatment effect is simply going to be y1 minus y0. But given what we discussed, y0 and y1 are counterfactuals of each other, right? So you can never measure both y1 and y0 at the same time and get your treatment effect. We can only measure one in a given time, and both cannot be observed. So this is the fundamental problem of causal inference. It makes it difficult to exactly measure treatment effects. But we need to understand the treatment effect in a whole slew of problems. So there should be some solutions around fundamental problem of causal inference. So one of these solutions is called temporal stability and causal transience. So what does that mean? Temporal stability means when you apply the treatment, it doesn't matter if you apply it today or tomorrow, it's going to have the same effect. So this does not apply in real life that much. So the treatment that you apply to a human, for example, has some temporal dependence. But let's say we apply a particular temperature on molecules of water. It is not depending on the mood that the water will freeze or not freeze. That is just continually the case. So it does not depend on time. Causal transience means whether the treatment that you apply is going to be reversible, right? So the unit undergoing treatment isn't able to reset back to its original setting. This, again, is something that happens in a lab. So for example, if I continually take headache pills, I will build up some sort of tolerance towards them. So the second option is unit homogeneity. What does this mean? This means when I take 2 units from my population, these 2 units are going to be identical. And so they're going to have the same reaction to the treatment. So this also is the case in lab settings. So if I take 2 molecules out of like, let's say a population of them, put one through the treatment, the other not through the treatment, I can observe Y1 and Y0 and get my treatment effect. But that is not the case with households undergoing pricing models or humans undergoing different treatments. And so lastly, a solution around the fundamental problem of causal inference is to estimate treatment effects using populations as opposed to units. In this problem, and in most problems involving humans and households, the third option can be used, but the first two options we cannot use. And so in this problem, the fundamental problem of causal inference makes it so that we need to analyze a population as opposed to a unit. And the larger the population, the more robustly we can estimate the treatment effect. In addition to that, if you have random samples of populations, it's going to help you remove the bias in this estimate. And so let's apply the same sort of framing that we've been thinking about for the problem at hand. So I have a subset of houses. They're going to go through the treatment being dynamic time of use pricing. And I want to understand the effect of this pricing model on their consumption during these high price points. So we need this other thing called the control group. In the control group, it is another subset of houses. In an ideal scenario, they're both random samples with a high number of households inside of them. And the reason that I need it goes back to control stability and causal transience. And so with a single group, because it is temporally dependent and because you cannot reset back to its original setting, you really can't use a single group to estimate this treatment effect. So for example, if I put a group of houses through dynamic time of use pricing, it is possible that I'm going to set some habits, and so the year after, even if they're not going through that, we are not resetting back to our original setting. So with this information, let's look at the trial that happened in London. So first of all, the trial is called Low Carbon London Smart Meter Trial. It came out of the Climate Change Act of 2008. So its motivation is policy-based. There's a number of projects that started as a result of this, and this is one of them. The data in the trial goes between late 2011 and early 2014. The treatment only took place in calendar year 2013. And we have half an hour level readings for the houses and the populations, and so that leads to about 167 million records. So we talked about dynamic time of use pricing, right? So we talked about the fact that the price bands are set, but the times are dynamic. So over on the left, you see the dynamic time of use pricing bands. So on the high level, you have 67 pence per kilowatt hour, and pence because this is in London. And in the normal and low hours, you have 11 and 4 pence per kilowatt hour. However, in the static pricing model, which is just the blank slate, when you're not going through the treatment, for the treatment group and at all times for the control group, you have 14 pence per kilowatt hour. So the high price point is quite high, but then the normal and the low are less than the static price point. Okay, so let's talk about the dynamic portion of this dynamic time of use pricing. So we know what the price bands are, we just don't know when they will be implemented. So the houses that went through this treatment got an at-home display. And in the middle, you'll see that they were notified 1 day before the price was implemented what times the price would be high. So similarly, they could get that over a text. And one thing to look at here is the first text says on the 15th, your electricity rate will be high between 5 a.m. and 8 a.m. On the 16th, they get a text that says on the 17th, the price will be high between 11 p.m. and 5 a.m. the next day. And so this is truly trying to understand how much people are willing to shift around their demand and how price sensitive they are. And so they were notified a day ahead, and we want to understand sort of their response to this dynamic high price point. The distribution for the high price point is pretty much equal. So mostly it happens at the end of day hours between 4 p.m. and 9 p.m. And this is the time they usually have a lot of demand on the grid. So that's fairly realistic, or at least the fact that it's not, it's more during the end of day hours. Our data set has two other features. One is the more granular socioeconomic category that you see. So Acorn is this consulting firm. They designate houses to different socioeconomic categories, and they've given 2 designations to the houses that exist in this trial. One is more granular than the other one. So this is the distribution. Over on the x-axis, you see the more granular version, and then the colors designate the less granular version. So you have adversity groups, affluent groups, and comfortable groups. Okay, so let's kind of try to understand our trial a bit more. How were people onboarded? How did people get into the treatment group? So the trial is double opt-in. What that means is that you have people, you have households, first of all, opting into sharing their data with you. And secondly, the treatment group opted into undergoing dynamic time of use pricing. In addition to that, in addition to the fact that they opted in, which could create some biases, there were some cash incentives that were provided to the treatment group. And so that in itself, you can kind of think about creating some biases in the population that opts into the treatment group. So you can kind of read through that quickly, but ultimately they could earn as much as £150 for being a part of the treatment group and completing the treatment. There were some measures taken by the people that designed the trial to make sure that the 2 groups are geographically balanced and also socioeconomically balanced. So we can remove that as being a source of bias. So the trial started in late 2011, right? And it went until early 2014. So over on the y-axis, you're getting a count of unique house IDs that exist in the data set. And so what this is showing here is that this is when they started the project. They're onboarding users up until early 2013, and that's kind of when the dynamic time of use pricing starts. And throughout 2013, some people drop out. And another thing to consider is that you have fewer houses in the treatment group versus the control group. And so as you're going through the onboarding process, you don't have as many houses as you go through time. So let's go back to the causality portion of this. You're analyzing populations, but your population is changing size in 2012. And so that could create some problems as you go through the analysis. So let's think about some reasons that the opt-in aspect could create some biases. So even though our groups are geographically and socioeconomically balanced, we can think of some reason that the opt-in aspect could create some biases, right? So let's think about some hypothetical reasons. It's possible that the group that opted into being part of the treatment group, they are more price sensitive than the other group. And so they're able to take advantage of this pricing model a bit more. It's possible then they're just low consuming groups. And another possibility is that those households have something about them, so like maybe their work hours, the work that they do, that they are able to sort of shift their demand around more easily than other households. Okay, so now that we know our trial, we have some understanding of causality, some understanding of the problem space, let's formulate a mathematical model. So let's designate our data into a control group and a treatment group, fairly intuitive designation. Let's also divide our data annually. And so we have alpha y being the control group's consumption matrix during the year y, and beta y being the treatment group's consumption matrix in the year y. Let's kind of think about these matrices. What numbers are in these matrices? So the alpha matrix is of size t by nc. The beta matrix is t by nt. So they have the time aspect first, and they have some n. And that n is the number of houses in the groups. And so t is all of those, we have half an hour measurements, right? So the t element is those half an hour measurements that we have for the year y. So for 2012 and 2013, where we have the full year, that's going to be just half an hour level intervals, 17,000 temporal components on the y-axis. And the n's are different, so going back to that plot, the control group is larger than the treatment group, so NC and NT is the only difference between these two matrices. Let's take beta hat 2013 to be the counterfactual consumption for beta 2013. So what is beta? Beta is the treatment group's consumption in 2013. That's the year they went through the treatment. And so going back to our understanding of what a counterfactual is, we want a counterfactual for this group to then be able to understand the impact of this pricing model, right? So we're just gonna note that as beta hat. So then our treatment effect is going to be beta hat minus beta, so that's going to be what it would have been minus what it actually was. And our goal here is to estimate beta hat. And so we are always trying to find a good estimate for the counterfactual, but that's always in service of finding a good estimate for the treatment effect. So let's think of a way we can estimate the counterfactual. So I have these two groups. They both didn't go through the treatment, and then one went through the treatment. And I'm trying to understand what could have been for the treatment group. And so why don't I just use the control group consumption? They both went, they geographic balance, right? So they both went through the same temperature in the year 2013. So why don't I use the alpha 2013 as the baseline for beta hat? So this would be great if the groups had the same baseline. And so we can check whether or not the groups have the same consumption patterns by looking at 2012 data. 2012, there's no impact of any sort of treatment. And so on the y-axis, you're seeing the average consumption per day for both of those groups. And so what this is showing is that the groups are not balanced, and on average, the treatment group is consuming less than the control group. And so if we had not looked at our data, and if we didn't know this about the trial, the fact that it was opt-in, this could change the dynamic of the consumption patterns of the groups, we could have falsely assumed that there's the same baseline, and then this could have actually led to the incorrect result, because if we have a lower consuming treatment group and we compare it with control group in 2013, you can actually conclude that the treatment group has lowered their consumption. But that's actually not as a result of the treatment, it is just because they consume less all the time. So turns out I can't use the other. So why don't I compare them to their own selves in the previous year, right? So now I want some counterfactual, some what would have been in 2013, but they actually went through static pricing in 2012, so I'll just use that data. So this is my more sophisticated naive model. But also, turns out that things change year over year. So in order to understand the change between 2012 and 2013, we're looking at the same metrics, so this is the average daily consumption for the control group. And so what this is showing is that during parts of the year, the 2013 consumption is more, and during times of the year, the 2012 consumption is more. So then again, we can't really use this as the baseline. So we've talked about two things. We've talked about the fact that the groups are not balanced. They do not have the same baseline behavior. And we've also talked about the fact that the 2 years created, there's a change between the years. And so this is going to give us two paths forward for estimating the counterfactual consumption. So this is the first path. So let's look at the boxes on the top. So if I take the consumption for the control group in 2012 and map it onto the consumption for the treatment group in 2012 and learn what that group mapping is from 2012 and apply it to 2013, I'm taking the same group, and let's assume this group mapping does not change over time. That's a simplifying assumption that I want to make. Then I can get the counterfactual consumption. So this is the first path. I am simply learning how to map one population onto another one to get the counterfactual consumption. Another way to do this is to learn this other thing that we looked at, right? Like, let's learn the changes based on time. So if I, again, learn the thing on the left, so let's use data from 2012 and 2013 for the control group, learn what the changes based on time is, then I can apply that to the treatment group and get the counterfactual consumption. So this shows you two methods of getting counterfactual consumption. I'm going to choose the first method. So this is just the mathematical formulation of that first method, right? So the first line is telling you that I have my control group matrix for 2012, and I have this x, that's my mapping function, and I have my control, so I want to map the control group onto the treatment group. So I can find x in the first line because I have data for 2012, and I can apply it to the second line to get the counterfactual consumption. So once I get an estimate for the counterfactual consumption, I can get an estimate for the treatment. Any questions? Cool. All right, so we've talked about these alpha matrices and beta matrices in abstract. So let's go fill out some data. But there's no alpha and beta matrix. So this is what the raw data looks like. It's actually delivered in 168 CSV files, and you have a couple of files for those features that I talked about, for the socioeconomic features and the tariffs that were implemented at different times. And so going back to the two lessons that I talked about, one reason that it's important to have some sort of mathematical model or framing is that it's going to inform how you want to read in and process your data. And so given the mathematical formulation that we just went through, I'm going to divide my data in a way that helps analyze using that model. So the first set of files that I'm going to create are going to hold only consumption values. So I want to create my alpha and beta matrices using these files. So I'm going to create files that have the unique house ID, whether or not it was in the treatment group, what half-an-hour interval we're talking about, and the consumption for that half-an-hour interval. The other file is going to be the socioeconomic features. So we haven't really talked about them that much, but it could be useful to bring them in at some point. So, and I have a unique house ID. So I'm going to store a file with the unique house ID and the two socioeconomic features that I have, and so that allows me to bring it in at any point that I want. And lastly, let's create the tariff file, right? So this is going to be the sort of mapper file that's going to tell you at this particular half-an-hour point in 2013, the pricing was low, high, or medium. And so this is going to help you because ultimately, let's go back to our original question. Our original question was, is this treatment effective in high prices? Because that is the way demand response would be using this pricing model. And so this third file is going to help us isolate what those hours are. Okay, so informed by the model, now I have these files. Look how much nicer that is. Okay, so let's go back to our model, right? This down here is the model that we had. X is going to be our group mapping. I can apply it, get the counterfactual, things are great. But let's go back to our onboarding process. So this is a plot that you've seen before. It's been made to parallel the matrix that we have. So our matrix, reminder, is a T by N. And so here again, we have a T. T is building up as the year goes along, and we have N, the number of unique houses. So let's go back to the onboarding process. So as 2012 is going along, they're bringing in more houses into the trial. And so what this says, kind of like parallelize these two pictures, actually your alpha 2012 matrix is half full. And that's also the case for your beta 2012 matrix. And so this both poses computational and sort of robustness issues, right? So if I'm going to learn my group mapping from two matrices that are actually half full, that's not going to give me a robust mapping. So there's some ways around this. I'm going to pose a couple of paths forward and then take one path forward. So one path forward is that I want to impute those values. So I have some missing values, but I have a lot of other values. So why don't I go learn something from the other values that I have and impute these values that I don't have? So there's one positive with this. There's a lot of positives, but one positive is that I get to keep a lot of the data that I have, right? So let's work off of the assumption that every data that I have, every data that I've aggregated or accumulated is useful. It's teaching you something useful. There's good trends that we can extract from that. And so that we can keep the data is a positive thing. But then this poses some challenges, right? So how do we impute the data? What imputation function do we use? Are we introducing any error? These are all questions that come with this method. Another path forward is let's limit the time frame. So there's the first half of 2012 where we're onboarding, but the latter half of 2012, we have a good fraction of our houses there. So why don't we just chop the data and look at the latter half of 2012, for example. So that, the limitation is going to be one of the themes that come up with these solutions. So the negative there is that you can't capture annual seasonality. And with electricity consumption, annual seasonality is a big deal, right? So there's definitely like an intuitive translation between what the temperature is like and what the electricity consumption is. And so if you limit that, you're not going to be able to capture the annual seasonality. Another path forward is let's fix a panel of houses. And so let me define some subset of rules for a house to pass through this filter, right? So let's, in the more strict scenario, say if a house has all of the 2012 data, they can enter my panel. And so I fix that panel, and only a subset of houses can enter that situation. And so what this means is that I'm getting rid of a lot of houses given the onboarding process. So again, we have this limitation, negative. But in addition to that, let's go back to our causality talk, right? So I want to study populations, but in order to robustly create an estimate, I want large populations. And this is going to get rid of a large fraction of the houses that I have. And lastly, another path forward is let's reduce dimensionality. And so we have these matrices that are of size t by n, but you can kind of shrink them, right? So why don't I define some metric, find a way to take it from n and turn it into a vector of size 1. And so what I can do is, for any given t, I have some number of houses for which I have a value. And so why don't I take the mean over all of the ones that I have to get a single representative value per half an hour for every given t during those years. And so, again, the negative here goes back to the same theme. So I will be getting rid of a lot of data, but I will be capturing some value in them, right? So I'm not getting rid of them entirely. I'm actually taking the mean along them. And so I can carry along some of the value that those data points have. So let's kind of think about how would you pick a path forward here? So there's really no wrong answer. It depends on the assumptions that you're comfortable making, and sort of the lesson, perhaps, is that you should make decisions that are informed by the data, but then also take into effect the kind of analysis that you want to do. Okay, so let's reduce dimensionality. So we have these matrices. They're of size t by nt, or nc, and we want to reduce them from this size to a vector of size t. And so what we're going to do is, for each given t, go take the average for the values that are there. So this is going to get rid of the n problem, as I call it. And so the fact that some of these t's have fewer houses than others really goes away in this situation, and then we end up with a vector of size t. And so we can rewrite our model using these vectors of size t. So nothing has really changed. Given the way the matrices were structured, all of them in this scenario will be of size t. And now my group mapping is a simple linear fit. So what I need to do is use 2012 data to learn A and B. So I'm just fitting a line. And I'm applying that same line to the 2013 data to get the counterfactual. Same story from there. I estimate the counterfactual, and I estimate the treatment effect. So this is what the line looks like. The data looks linear, so that's good. But we have this offshoot here. And we, and with more time, it would be good to try and understand what this offshoot is. And so sort of like another lesson is, let's say you pick a model, you apply it, and you observe something that doesn't exactly match what you expected. It's good to go back and check, figure out what is this offshoot that you have, or maybe is a linear model a good choice in this situation. But let's see if we can do a little bit better than that. So let's go back to our matrix. So we have these values t, we're building up, but also we have unique house IDs. And we have socioeconomic features for these house IDs. So let me see if I can kind of use those features to see if the impact of this pricing model was different between the different socioeconomic groups. And so I can divide my matrix into different socioeconomic categories because I have the unique house IDs and I know what the socioeconomic value is, socioeconomic category is for those. And so with that, I can, instead of fitting one line, fit 3 lines. So it's the same linear fit. I'm now just dividing the matrices into socioeconomic subcategories and then doing that dimensionality reduction on each of those socioeconomic groups. And so these are the different lines that you're getting. They're not that different, but they're different. They all have that option. So, you can apply the line on your 2013 data to get that counterfactual, and now you have an estimate for your treatment. So this is what your treatment estimate looks like. It is also a vector of size t, but let's go back to the original question. The original question was, what is the effect of this treatment on high price hours? And so one of the other files that we had is a tariff file. So I know per half an hour in 2013 what price was implemented. And so the goal is for me to understand, more importantly, the effect of this pricing model on the high price hours. Okay, so in the title I had something about Python and mathematical modeling. We've been talking a lot about mathematical modeling, but where's the Python in all this? So to me, which kind of this ties back to the second point of the talk, Python is a very useful tool. So the mapping between matrices and vectors, which is what we've been talking about, to Python is fairly intuitive. But also it's important to ground your work in a mathematical model and mathematical framing, and then the Python will just sort of like flow from there. But let's talk about a particular case where the Python is very useful. So T adversity is that treatment estimate of size T. So going back to 365 times 48, that's the 17,520. And so that is my treatment estimate vector of size T. And the thing that I want to learn, let's go back to the previous picture, is I want to isolate to the time intervals that had high price points. And so I also have a file that tells me what the tariffs are at any given point in time. So this highs, it's going to tell me the half an hour intervals that had high price points. And so what I want to do is go to my vector of size t and find only those intervals that had high price points and find what the treatment effect is there. So I can do that very easily using a pandas series. So I'm turning my column vector into a row vector using this reshape. And I'm passing in the index that has half an hour intervals for 2013. And with that, I can simply look up, do a dot look, and look up the time intervals that have high price points. And so now I can conclude that there was 12% shedding in those times. This is already in percent space, so I'm taking the mean over all of those high half an hours. And so getting a single value for the treatment effect for the adversity group, multiplying by 100 just to take it into percent space. Any questions there? So what pandas allows for me to do is that you can use pandas very easily with time series data. And so I could do this, if I didn't have pandas, it would take much longer, it would be more difficult. So here are some results. So we have our 3 socioeconomic categories, and we have our 3 segmentation of price. Overall, just takes everything into one cup. But let's go back to the original question again. We care about the impact during these high price points. And so on average, the adversity and comfortable group have shed demand by 12%, and the affluent group has shed demand by 4.51%. So here we can conclude that going back to the effectiveness metric that we defined for this pricing model, that our treatment was effective in lowering consumption in the times of high demand. So let's go back to the lessons. So there were a lot of decisions that we made throughout this journey. A lot of them were informed by our knowledge of the data. So the fact that it was opt-in, the fact that there was a fill rate issue, and the fact that we have larger populations, and so it's both on the negative side, so understanding the shortfalls and the biases, but also understanding the strengths of your data is going to help you guide the analysis steps forward, and it is important to do that. And so secondly, I'm almost done. Secondly, it is important to have some model grounded in real world and guided by first principles, and then jump into the data and try to fit a model to your data. And so that's that diagram. You start from reality. You have some understanding of the mathematical framework that you want to apply, and that guides both your analysis, but then also how you clean up your data and how you construct your data. So with that, if you want to learn more, that's my thesis.